Let's start with the basics. An algorithm is really just a detailed, step-by-step instruction set. Imagine you're making a cake. That recipe is an algorithm. It tells you exactly what to do in order and gives you the final result. Algorithms take some input, like ingredients, and they produce a specific output, which is a delicious cake. They also need to have a clear, defined sequence of steps and must always finish after a certain number of instructions. Okay, so after writing up your algorithm, it's really important to step back and ask yourself, is this asterisk actually asterisk good? There are a few key things to consider. First off, it absolutely has to be correct, meaning it gives you the right answer every time for valid inputs. Then we need to think about how fast it runs. That's called time complexity, measured using something called Big O notation. Similarly, we want to keep an eye on how much memory it uses, which is space complexity. Beyond performance, a good algorithm should also be easy to read and understand. Clear code is super important for maintainability. Finally, can your algorithm handle big amounts of data? That's scalability. You don't want something that works great for small datasets but falls apart when it gets bigger. Let's talk about time complexity. Basically, it's a way to describe how quickly an algorithm runs. It doesn't tell you the exact time, but instead how the runtime grows as you give it more and more information. We use something called Big O notation. Think of it like shorthand for describing efficiency. It helps us understand that some algorithms are much faster than others when dealing with large datasets. For example, accessing an item in a list is usually pretty quick constant time. As the list gets bigger, algorithms that involve loops can take longer, scaling linearly or even quadratically, which we want to avoid for big data. Okay, let's talk about space complexity. It's a really important concept when we're thinking about how efficient our algorithms are. Simply put, space complexity tells us how much memory an algorithm needs to run beyond just the size of the data it's working with. There are two main things to consider: auxiliary space, which is extra memory used by the algorithm itself, and the space needed for the input data. We often express this using Big O notation, looking at the upper limit of how much memory could be used. Algorithms like simple function calls use constant space, while storing an array directly requires linear space. And when you start using nested loops to process data, quadratic space complexity can kick in. Understanding these different levels helps us choose the best algorithm for a particular task. Okay, let's talk about something super important in algorithms: Big O notation. Basically, it's a shorthand way to describe how an algorithm performs as the data gets bigger and bigger. Think of it like this: you don't need to know exactly how long an algorithm takes for a small input. Big O tells you how quickly it will slow down if you give it a huge amount of data. It focuses on the worst case scenario, so we always have a sense of how scalable the algorithm is. We'll look at some common examples: constant time, logarithmic, linear, and quadratic, and you'll see how they scale as the input grows. Ultimately, algorithms with low Big O values are almost always more efficient. Okay, let's talk about how we measure the efficiency of our algorithms, specifically time complexity. Basically, it tells us how the runtime of an algorithm changes as the amount of data it has to work with gets bigger. We categorize this into different classes. First up is Zoon, which means constant time. The execution time stays the same no matter how much data you throw at it. Then we have logarithmic time, or log n, which is super efficient. Think about searching a sorted list using binary search. It gets faster and faster as the list grows. Linear time, on, just means the runtime increases proportionally to the size of your input. You'll see this when you're looping through an array once. Next up, on log n, often found in efficient sorting algorithms like merge sort. We also have quadratic time, on squared, where things start to slow down noticeably as your data grows, typically caused by nested loops. Finally, exponential time, alt1, is something to really avoid. It can become incredibly slow very quickly. Understanding these classes helps you choose the right algorithm for the job and predict how well it'll perform with large datasets. Okay, let's talk about how we measure the speed of an algorithm. We use something called time complexity. Two important notations here are on, which is linear time, and log n, which is logarithmic time. Linear time means that if you double the amount of data you're working with, your processing time doubles too. It's straightforward. Logarithmic time, on the other hand, is much more efficient for large datasets. Imagine searching a phone book. Binary search log n quickly narrows down possibilities by half in each step, whereas linear search would check every single name. Logarithmic timescales much slower as data grows, making it ideal when you're dealing with huge amounts of information. Okay, let's talk about brute force algorithms. These are basically the try-everything approach to solving a problem. They're often the first thing we think of because they are easy to write initially. Imagine you're searching for a specific number in a list. A brute force algorithm would just go through every single number in that list until it finds what you're looking for or reaches the end. It works great for small lists, but as the list gets bigger, it can become incredibly slow and inefficient because it has to check every possibility. It's a really basic strategy. Think of it like systematically checking every single option, no matter how time-consuming. Okay, let's talk about recursive algorithms. They're a really cool concept in programming. They're basically functions that call themselves. Think of it like Russian nesting dolls. Each doll contains a smaller version of itself. To do this effectively, we need two things: a base case, which is the simplest scenario where the function just knows what to return without needing to call itself again, and a recursive step. This is where the function calls itself with slightly modified inputs, slowly working its way toward that base case. Okay, let's talk about iterative algorithms. Essentially, they are all about repetition, using loops to repeat a set of instructions until we get the result we need. It's like following a recipe step by step, adjusting things slightly each time. Unlike recursive algorithms that call themselves over and over again, iterative approaches use for a while loops to keep track of what's happening. They tend to be more efficient when it comes to memory, which is a big plus in many coding scenarios. Let's look at an example calculating the factorial of a number using a simple loop. Okay, let's talk about greedy algorithms. Think of them like making quick decisions. You're focusing on what looks best right now without worrying too much about how it might affect things later. They are a really common technique in computer science, especially when we need a fast solution and don't necessarily need the absolute best one. They make choices step by step, always picking the option that seems best at that exact moment, like taking the shortest path on a map without looking ahead to see if there's a better route further down the road. While they are often simple and efficient, it's important to remember they don't always guarantee the optimal solution, so it's good to be aware of that. Okay, let's talk about divide and conquer. It's a really smart way of tackling complex problems. Think of it like breaking down a massive task into smaller, easier to handle pieces, like slicing a big cake. You solve these little sub-problems independently and then put them back together to get the final answer. Merge sort, quick sort, and even binary search are great examples of algorithms that use this technique. They often lead to really efficient solutions, especially when dealing with large data sets. Okay, let's talk about dynamic programming. It's a really clever technique in algorithms. Basically, it tackles big problems by breaking them down into smaller pieces that we've already solved and we don't have to solve them again. The key idea is that if you want the best answer to the whole problem, each of those little parts also needs to be the best possible solution. And often, these little parts overlap, meaning we're tackling the same questions multiple times in a standard approach. Dynamic programming avoids this repetition by storing our answers so we can just reuse them when needed. We use two main methods: memoization, which is like thinking recursively and remembering what you've already done, or tabulation, which is building up all the solutions from the ground up. Okay, let's talk about memoization. It's a really clever trick for making recursive algorithms run faster. Think of it like this: sometimes, when you call a function that calls itself repeatedly with the same inputs, you end up doing the exact same calculations over and over again. Memoization prevents this. It uses a little cache. Think of it like a memory bank to store the results of those calculations. So, before your function does any work, it checks if the answer is already in that cache. If it is, great, you just grab it and return it instantly. If not, you calculate the result, save it in the cache for later use, then give you the answer. It's a fantastic way to avoid repeating yourself and dramatically improve performance. Okay, let's tackle dynamic programming and divide and conquer. They are both super useful in algorithms, but work differently. Think of dynamic programming like building a staircase, one step at a time. You solve smaller parts first and store the solutions so you don't have to recalculate them later. It's great for optimization problems where you want to find the best solution. On the other hand, divide and conquer is more like breaking down a giant puzzle into smaller pieces. You tackle each piece independently and then put them all together at the end. It often uses recursion to handle this splitting. While it can be very powerful, it can sometimes lead to slower performance if not carefully optimized. Both techniques are valuable tools in your algorithmic toolbox. Okay, let's talk about backtracking. It's a really clever technique used to solve problems where you need to try out lots of different possibilities. Think of it like exploring a maze. You take one path, and if you hit a dead end, you go back and try another route. The core idea is that you build up your solutions step by step, but if you realize something isn't going to work, you don't waste time continuing down that path. Instead, you backtrack and try something else. It's especially handy when dealing with problems like Sudoku or mazes where there are tons of potential options. Okay, let's start with the basics. A sorting algorithm is simply a set of instructions that helps us arrange things in a specific order, like putting a deck of cards in numerical sequence. It's incredibly useful in computer science because we often need to sort data, whether it's names, numbers, or even web pages, so we can easily find what we're looking for. There are all sorts of different ways to do this, and each one has its own advantages depending on the situation. Okay, let's talk about sorting algorithms. These are really important for organizing data efficiently. Think of it like tidying up your code or a database. We've got some familiar ones here. Bubble sort is straightforward but not super fast. Insertion sort builds the sorted list step by step. Selection sort finds the best element repeatedly and swaps them around. Then we have merge sort, which breaks things down into smaller pieces to sort them perfectly, and quick sort. This one's often a favorite because it's usually quite speedy in practice. Okay, let's talk about how fast quick sort actually is. In general, it's a really great sorting algorithm. We say it has a time complexity of on log n in the best and average cases. That means as your data size grows, the time to sort it increases proportionally to the square root of that size. However, there's a downside. If you happen to pick a bad pivot element, like when your data is already sorted or nearly sorted, the algorithm can degrade to unsquared, which isn't ideal. But with smart pivot selection, quicksort usually performs exceptionally well and remains one of the fastest sorting algorithms in practice. Okay, let's talk about merge sort. This algorithm is known for being really dependable in terms of how quickly it sorts things. Its time complexity, basically how long it takes to sort a list, is consistently on log n. That means as the size of your data grows, the sorting time increases proportionally to n times log n. It's the same for best, average, and worst case scenarios, which is fantastic. The reason for this efficiency is its clever divide and conquer strategy. It breaks down large problems into smaller ones, making it very predictable. Okay, let's talk about quick sort and merge sort. Both are super popular sorting algorithms, but they approach things in different ways. Quick sort is like a clever trick where we pick an element to be a pivot and then rearrange everything around it. It's usually really fast, close to on log n on average, but if you choose a pivot poorly, it can slow down to unsquared. Merge sort, on the other hand, is more methodical. It breaks the problem down into smaller pieces until each piece has only one item, and then carefully merges those sorted pieces back together. This guarantees that it'll always perform around on log n, no matter what kind of data you're sorting. Merge sort also tends to require a bit more memory because it needs space to hold the merged subarrays. Thinking about stability is important too. Quick sort isn't stable, meaning it might shuffle equal elements around, while merge sort ** is ** stable, preserving their original order. Okay, let's talk about how bubble sort and insertion sort stack up against each other. Both are simple sorting algorithms, but they work in different ways. Bubble sort repeatedly compares adjacent elements and swaps them if they're out of order. Think of larger elements slowly rising to the top like bubbles. It's easy to code, but it can be slow for bigger lists because it has a quadratic time complexity. Insertion sort, on the other hand, builds a sorted portion of the array by inserting each element into its correct place within that sorted part. This is efficient when your data is almost sorted or nearly sorted already, and also has a quadratic time complexity. Generally, insertion sort tends to be more stable and perform better than bubble sort for larger datasets. Okay, let's talk about searching algorithms. They're a really important building block in computer science. Think of them as your detective tools for finding specific information within a bigger collection of data. They provide a structured way to look through everything until you find what you're after. It's all about efficiency and choosing the right algorithm depending on how big the data set is and the type of data structure it's stored in. Some basic examples include linear search, which is straightforward but can be slow for large amounts of data, and binary search, which is much faster if your data is already sorted. Okay, let's talk about searching algorithms. We'll start with linear search. It's really straightforward. You just go through each item in a list one by one until you either find your target or reach the end. It's simple to understand, but can be slower if the list is huge. Now, binary search is a completely different beast. Because the data is sorted, we can repeatedly divide the search area in half. Think of it like a game of guess where we keep eliminating half the possibilities until we pinpoint the exact location. The main benefit? It's much faster for large lists because it doesn't have to check every single element. Okay, let's talk about binary search and its time complexity. Binary search is a fantastic algorithm for quickly finding items in sorted data. It works by repeatedly dividing the search area in half. Imagine splitting a book in two each time. Because of this division, it has a really impressive time complexity of O log n. That means that as your data gets bigger, the number of steps it takes to find something grows much slower than just linearly. It's like cutting a cake. You don't have to try every slice individually, you keep eliminating parts until you reach what you're looking for. Understanding this logarithmic complexity is really important when discussing algorithm efficiency in interviews. Okay, let's talk about graph algorithms. Essentially, they're a way of tackling problems when you can represent things and their relationships as a network nodes connected by edges. Think of it like friends on social media. Each person is a node, and the connection between them is an edge. There are several key algorithms, like breadth-first search, which finds the shortest path level by level, or depth-first search that explores deeply before backing up. We also have Dijkstra's to find shortest paths in graphs with positive weights, and Bellman-Ford for handling negative weights. These algorithms are used everywhere, from figuring out the best route on a map to analyzing how information spreads through a network. Let's move on to explore some specific examples. Okay, let's talk about breadth-first search, or BFS. It's a really common algorithm used when we need to explore all the nodes in a graph like a map. Basically, it works by systematically visiting nodes level by level, just like ripples spreading out from a point in water. We use a queue to keep track of which nodes we should visit next, and we always explore everything at the current depth before moving down to the next layer. It's great for finding the shortest path between 2 points if all the edges have the same weight. Okay, let's talk about depth-first search. It's a really common algorithm you'll encounter in interviews, and it's surprisingly simple to understand. Basically, DFS is like exploring a maze. You pick a path and go as far as you can down that route. If you hit a dead end, you turn around and try another path. It systematically visits every node reachable from the starting point before moving on. You'll typically implement it using either a stack or by calling the algorithm recursively for each unvisited neighbor. Okay, let's talk about Dijkstra's algorithm. It's a really powerful tool for figuring out the quickest way to get around in a network. Think of it like finding the best route on Google Maps. Essentially, It's designed to find the shortest path from one starting point to all other points in a graph where the distances between those points are all positive. It works by starting with the beginning node and constantly checking its neighbors, always picking the closest one to explore next. It keeps track of how far each node is from the start and updates that distance whenever it finds a shorter path. It's like a smart explorer systematically covering the entire network. Okay, let's talk about asterisk search. It's a really clever way of finding the best route through a map or graph. Think of it like navigating with a GPS. You don't just explore every possible path randomly, you use an estimate to focus on the most promising ones. Asterisk keeps track of nodes it's already checked closed set and those that need checking open set. It calculates a score for each node based on how far away it is from the starting point g-cost and then uses a heuristic, essentially an educated guess about how far it is to the destination. The algorithm always chooses to explore nodes with the lowest overall score, making it much faster than other methods in many situations, as long as your estimate isn't too optimistic. Okay, let's talk about spanning trees. Imagine you have a map of cities and want to connect them with roads and network. A spanning tree is like finding the smallest set of roads that connects every single city without creating any loops or circles in the road system. It's a really important concept in graph theory, and algorithms like Kruskal's and Prims are used to find these minimal connecting paths efficiently. They are super useful for things like routing data or designing networks. Okay, let's talk about Kruskal's algorithm, a really clever way to find the shortest possible connections between different parts of a network. Imagine you need to build roads across a country and want to do it in the most cost-effective way. Kruskal's algorithm helps you figure out which roads to build. Essentially, it's a greedy approach. We always pick the cheapest road available that doesn't create a loop, so no going back and forth between the same places. It starts by listing all possible connections in order of how much they cost, then works its way through them, adding each one if it doesn't make the network circular. The key is using something called disjoint set union to efficiently check for cycles as we build the tree. Okay, let's talk about Prim's algorithm. It's a really useful tool in graph theory, and it's a common question you might see in coding interviews. Basically, it helps us find the cheapest way to connect all the points on a map or vertices in a network without creating any loops. It works by starting with a single point and constantly adding the lowest cost edge that connects a visited point to an unvisited one until every point is connected. It's a greedy algorithm, meaning it makes what seems like the best choice at each step, which guarantees we'll end up with the minimum spanning tree. Let's talk hashing algorithms. Basically, they're like digital fingerprint machines. You feed any piece of data into a hashing algorithm. It could be text, numbers, anything really, and it spits out a fixed size output called a hash value. This hash acts as the unique identifier for the data. It's important to remember that the same input always produces the same hash, making it deterministic. And because they are designed to be fast, hashing algorithms are super useful in various computer applications. They aim to ensure different inputs yield different hashes. We call this collision resistance, so collisions can sometimes happen. Okay, so hashing is all about quickly finding things in a data structure. The goal is that each key gets assigned a unique spot. But here's the thing, it's possible for two different keys to end up with the exact same address. That's a collision. It's like having two people with the same ID number in a system designed to uniquely identify everyone. When we encounter a collision, we need a strategy to deal with it, usually by adding more information about the item or searching for another available spot. Okay, let's talk about hash tables. Think of them as a really fast way to store and retrieve information. Basically, they're like a super organized address book where each item has a unique key that helps us find it quickly. A special function called the hash function converts the key into an index, a location in the table. If two different keys happen to get the same index, that's called a collision. We use clever methods to handle it and still find what we need. Hash tables are amazing because, on average, finding, adding, or removing something takes just about as long as it takes to type the key. That's why they're so useful in things like caching and databases. Okay, let's talk about how hash tables handle those pesky collisions. There are two main ways to do it: separate chaining and open addressing. Separate chaining is like having a little mailbox for each key. When you try to put something in a slot that's already taken, you just add it to the list associated with that slot. It's pretty straightforward, but it uses extra space for those lists. Open addressing, on the other hand, is more compact. Instead of using separate data structures, it probes around the hash table itself until it finds an empty spot where a collision happens. There are different strategies for this probing: linear, quadratic, and double hashing, each with its own trade-offs. Open addressing can be faster if you don't have too many collisions, but it's prone to clustering, which can slow things down. Okay, let's talk about string matching algorithms. Basically, they're all about finding where a specific pattern appears within a larger piece of text. Imagine you're looking for a word in a really long book. That's what we're trying to do efficiently here. There are several approaches. The simplest is called naive string matching, which just checks every possible position, but it can be slow. Then there's KMP and Boyer-Moore, which use smarter techniques to speed things up. Knowing these different methods will definitely help you if a string matching problem comes up in an interview. Okay, let's talk about the KMP algorithm. It's a clever way to efficiently find patterns within larger texts. Think of it like this: instead of starting from scratch every time you hit a mismatch, the KMP algorithm uses some pre-calculated information about the pattern itself. Specifically, it creates what we call an LPS array, which essentially tells us how much overlap there is between prefixes and suffixes of the pattern. This allows us to skip over large portions of the text when searching, making it significantly faster than a basic approach. The time complexity is really impressive on +n, where m is the length of the pattern and n is the length of the text. Let's dive into the Rabin-Karp algorithm, a clever way to find patterns within text. Essentially, it uses hashing to speed up the process. First, we hash our pattern string to get a unique number. Then, we hash the first slice of the larger text that's the same length as the pattern. If those two hashes match, we check to make sure they actually match character by character, because sometimes different strings can have the same hash value collision. And then, sliding the window through the rest of the text using a rolling hash function allows us to update the text's hash efficiently without having to recompute it from scratch each time. It's like a fast and smart way to search. Okay, let's talk about heaps. Essentially, a heap is like an organized tree structure where the largest or smallest element is always at the top. It's climbing to the top. It's really handy for things like priority queues, where you need to process items in order of importance. Think of it like a to-do list, where urgent tasks are handled first. And heaps aren't just good for queues, they also form the backbone of efficient sorting algorithms like heap sort, and even play a role in finding shortest paths in graphs. Okay, let's talk about topological sort. It's all about figuring out the correct order to complete a set of tasks when those tasks have dependencies on each other, meaning some things have to happen before others. We're dealing with directed acyclic graphs here, which means no loops or cycles. If there were, we couldn't determine a valid order. Imagine you're building a house. You need the foundation before you can put up the walls, and then the roof. Topological sort helps us map out that sequence of steps. Okay, let's talk about two-pointer techniques. They are seriously useful when dealing with sorted data in interviews. Basically, it's a strategy for quickly finding things within that data. Imagine you have a list of numbers already arranged in order, and you need to find if there's a pair that adds up to a certain value, or maybe identify the first and last position of an element. The core idea is to use two pointers, one starting at the beginning and another at the end of your data structure. You compare what the pointer and then adjust them based on what you're looking for, moving either pointer closer to where you think the solution might be. It's a really efficient way to tackle these kinds of problems. Okay, let's talk about sliding window algorithms. These are really handy tools for tackling data challenges where you're looking at chunks or windows of a bigger data set. Instead of re-evaluating everything each time, we keep a window and slide it along, efficiently recalculating results based on the new position. Think of it like scanning a document. You don't read every single word again, you just move your eye across the page. This is especially useful when dealing with massive amounts of data or continuous streams where you can't load everything into memory at once. Okay, let's talk about Floyd's algorithm, a really cool trick for finding cycles in linked lists. It's like having two runners on a track, one slow and steady, the tortoise, and another super fast, the hare. If there's a loop or cycle in the list, the hare will eventually lap the tortoise. If there isn't a cycle, the hare just runs until it hits the end of the list. It's amazingly efficient. It only takes us through each node once and uses very little memory. Okay, let's talk about calculating factorials, a classic interview question. There are two common ways to do this, recursively and iteratively. Recursion is like defining the problem in terms of itself. It's quite elegant but can run into issues if you try to calculate factorials of very large numbers because it uses up all the computer's memory. The iterative approach, on the other hand, just uses a loop to repeatedly multiply numbers together. It's usually more efficient and doesn't have that memory problem, making it a safer bet for larger inputs. Okay, let's talk about how we classify computational problems. We start with NP, non-deterministic polynomial time. These are problems where you can quickly check if a solution is correct, but finding the solution itself might be tricky. Then we have NP complete problems, which are like the heavy hitters within NP. They're incredibly hard to solve, and any algorithm that solves one must also solve all others in NP. Finally, there's NP hard, which is an even broader category, problems that are at least as difficult as any problem in NP but might not have a quick verification method. Essentially, they are some of the toughest challenges we face when designing algorithms. Okay, let's talk about the traveling salesman problem, a really interesting one you often see in algorithm interviews. Think of it like this. You've got a salesman who needs to visit several cities and then head back home. The challenge is figuring out which route he takes to minimize his total travel distance. It's an optimization problem, meaning we want to find the best possible solution, the shortest route in this case. Now, here's the tricky part. It turns out that finding the absolute shortest path for a large number of cities can be incredibly difficult. It's considered NP hard, which means there isn't an easy way to solve it efficiently. So, interviewers often ask you about how you would approach this kind of problem, and remember, there are lots of different strategies you could consider depending on the size of the problem. Let's talk about dynamic connectivity. It's a clever trick for handling graphs where connections are constantly changing. Basically, we need to quickly check if two nodes are still connected, even as the network evolves. The secret weapon here is union find, also known as disjoint set. Think of each set in the union find data structure as representing a group of interconnected nodes, a connected component. When you add or remove a connection, we use union to merge or split these groups. So, find tells us which group a node belongs to, and that's all we need for quick connectivity checks. Thank you for watching.